Hello friends, I already have discussed about electrons and holes. In this lecture, I am going to introduce another important concept of electron and hole-like Fermi surface and electron and hole-like orbit. The concept of electron and hole orbit is going to explain the anomalous Hall coefficient observed in divalent, trivalent, and tetravalent metals. If we just have an external magnetic field, then equations of motion are given by this and this. Let us calculate dk dt dot b, which is equal to which is equal to 0. Thus, component of K parallel to B does not change with time, or in other words, component of K along the magnetic field is a constant of motion. Next, we calculate dk dt dot v, where v is the velocity. This is equal to which is equal to 0. Since v is gradient of energy, this equation implies that energy is also a constant of motion. In conclusion, in a uniform magnetic field, component of K along the magnetic field is a constant of motion and electronic energy is a constant of motion. Let us consider a free electron-like constant energy surface spherical in shape and understand the consequences of two constants of motion considering a uniform external magnetic field. However, what we are going to discuss will remain valid even if the constant energy surface is not spherical. Magnetic field is in this direction. Since component of K along the magnetic field does not change with time, the electron orbit must be confined to a plane perpendicular to the external magnetic field, that is this plane. Moreover, since energy is also a constant of motion, the electron orbit has to stay on the constant energy surface. In this case, a spherical surface. Thus, in K space, trajectory along a curve is given by the intersection of a constant energy surface, which is spherical in this case, and a plane perpendicular to B, which is marked by blue lines in this diagram. The trajectory of electron is along the red curve. In case of electron, gradient of energy points away from the center, and the trajectory is anti-clockwise. This is known as electron-like orbit. A hole is positively charged and its orbit is clockwise in a magnetic field. In case of a hole orbit, gradient of energy points towards the center. We know that in a static magnetic field, electrons move on a curve determined by the intersection of a constant energy surface and a plane perpendicular to the constant energy surface. It makes sense to take the constant energy surface to be the Fermi surface. Let us take a 2D Fermi surface and consider the magnetic field to be out of the plane. In these figures, the shaded regions are occupied and the unshaded regions are unoccupied states. The closed orbits in this figure and in this figure are traversed in opposite directions. Since particles having opposite charge orbit in a magnetic field in opposite sense, we call this orbit as electron-like and this orbit as hole-like. In electron-like orbit, wave vector change in a counterclockwise direction. In hole-like orbit, wave vector change in a clockwise direction. An electron in hole-like orbit moves as if it has a positive charge. Note that dk dt is perpendicular to the gradient of energy. So, if we draw the gradient first, we can easily find out the orbit in K space. Is there any rule to draw the gradient of energy? You have to keep in mind that the gradient points from filled to empty levels and lower to higher energy. Note that if the Fermi surface encloses filled states, it is an electron-like Fermi surface and the orbit is electron-like orbit. On the other hand, if the Fermi surface encloses unoccupied states, it is a hole-like Fermi surface and the orbit is hole-like orbit. Whatever we have discussed applies to Fermi surface of any shape. For example, take a hypothetical 2D tetravalent metal. I have already shown how to draw the free electron Fermi surface for a 2D tetravalent metal. This is how the Fermi surface looks like in the second Brillouin zone, and this is how it looks like in the third Brillouin zone. The first Brillouin zone is completely full and not shown here. In second Brillouin zone, we have a hole-like Fermi surface. This is the gradient and dk dt points in this direction. In third Brillouin zone, we have a electron-like Fermi surface. This is the gradient and dk dt points in this direction. Let us consider a divalent metal. We already know how to draw the Fermi surface of a divalent metal. This is how it looks like in extended zone scheme. Part of the Fermi surface lies in the first Brillouin zone and rest of it in the second Brillouin zone. If we repeat periodically in reciprocal space, this is how it looks like in the first Brillouin zone and this is how it looks like in the second Brillouin zone. Clearly, there are vacant sites near the corner of an almost filled band. As a result, we get a hole-like Fermi surface in the first Brillouin zone. Note that Fermi surface is enclosing empty states in this case. On the other hand, there are some occupied states in the second Brillouin zone. As a result, we get an electron-like Fermi surface in second Brillouin zone. Note that Fermi surface is enclosing filled states in this case. Obviously, completely electron-like Fermi surface can exist only in case of monovalent metals because Fermi surface does not cross the first Brillouin zone boundary in this case. In case of divalent, trivalent or tetravalent metals, part of the Fermi surface is electron-like and part of it is hole-like. In case the Fermi surface is hole-like, an electron in hole-like orbit moves as if it has a positive charge. This must be related to the anomalous Hall coefficient in divalent, trivalent, or tetravalent metals. So far, we have been discussing electron orbit in the K space. Let us now discuss about electron orbit in real space. In the presence of a static magnetic field, equation of motion is h cross dk dt is equals to minus E by C B cross D. Now we express the vector B in terms of its magnitude and unit vector in the direction of D, such that this equation is minus E B divided by C B cross B hat. Let me call this as equation 1. Velocity V is equals to dr by dt. Let me call this as equation 2. In equation 1, we take a cross product with B such that the left hand side is h bar B hat cross dk dt is equals to minus EB by C B hat cross B cross B, which is equal to minus EB by C B hat dot B hat B minus B hat dot V B hat. Let me call this as equation 3. As shown in this diagram, the blue plane is perpendicular to the direction of external magnetic field. We want to get the projection of R space orbit, which is shown by this black line in this plane, which is perpendicular to the external magnetic field. Thus, we want real space orbit in a plane perpendicular to D. In this case, B hat dot V is equals to 0. So this term is 0. Then from equation 3, we get h bar B hat cross dk dt is equals to minus EB by C, and in place of V, I just write dr dt. Since R is lying in a plane which is perpendicular to the external magnetic field, I write a small subscript perpendicular. Finally, we can write it as dr perpendicular dt is equals to minus h bar c divided by EB b hat cross dk dt. Thus, projection of the R space orbit in a plane perpendicular to the field can be obtained from the K space orbit. Finally, let us apply simultaneous magnetic and electric field. Assume magnetic field along the z direction and electric field along the x direction. This is same as our Hall effect discussion. The equation of motion is h bar dk dt is equals to minus E times the electric field minus E by C V cross B. Now, this vector, I write it as magnitude times the unit vector. Similarly, this vector, I write it as its magnitude times the unit vector. And then we can rewrite the equation as minus E times E hat minus E B divided by C V cross B hat. Let me call this as equation 1. We know that dr dt is equals to V. I call this as equation 2. Now, in equation 1, I take cross product with B hat such that the left hand side is H cross B hat cross dk dt is equals to minus E times capital E B hat cross E hat minus EB by C B hat cross V cross B hat. And this is equal to minus E B hat cross E hat minus EB by C B hat dot B hat V minus B hat dot V B hat. Let me call this as equation 3. Now, as explained in the previous slide, we want real space orbit in a plane perpendicular to B such that B hat dot B is equals to 0. So this term is 0 in equation 3. Thus, from equation 3, we get H bar B hat cross dk dt is equals to minus E times capital E B hat cross E hat minus EB by C. B hat dot B hat is 1, and in place of V I just write dr dt. Since R is a vector lying in a plane perpendicular to B, I just write a small subscript perpendicular. Thus, we get dr perpendicular dt is equals to minus h bar c divided by E times B hat cross dk dt minus C times E divided by B hat cross E hat. Solving this equation, we get R perpendicular at time t minus R perpendicular at time 0 is equals to minus h bar c divided by E times B hat cross k of t minus k of 0 minus C E divided by B hat cross E times T. So, we are considering a case of applying uniform electric field in addition to the static magnetic field. This is how position of electron is changing in a plane perpendicular to the magnetic field. Motion has two parts. The orbital part, as it would be if only magnetic field is present. In addition to the orbital part, we have a uniform drift term with drift velocity Vd is equals to C by B times electric field cross B hat. In steady state, we have to replace T with relaxation time tau. And we also assume that the electron is completing several orbits between two collisions. We know that if only magnetic field is applied, the electron is doing orbital motion in k space as well. So, this term is bounded in time as k is along an orbit. Thus, the drift term has dominant contribution. Now, let us consider current density for electrons. J equal to minus NE times the drift velocity. The drift velocity is given by this equation, such that the current density can be written in this form. Similarly, current density for holes is given by J is equals to NH times E times Vd, where NH is the density of holes and Vd is the drift velocity, which is given by this equation, such that the current density for holes can be written as this. Assume the magnetic field to be in Z direction. An electric field is applied in the X direction, and as a result of Lorentz force, a transverse electric field, builds up in the y direction. If we just take the x component from both sides of this equation, then we get Jx equal to minus NEC times Ey by Bz, which can be rewritten as Ey by Jx Bz, which is equal to the Hall coefficient, which is equal to minus 1 by NEC. Similarly, by equating the x component from both sides of this equation, we get Jx equal to NH times E times C times Ey by Bz for holes, which implies that the Hall coefficient for holes is given by RH is equals to 1 by NHEC. Thus, Hall coefficient for electron and hole have opposite sign. Now, if several bands contribute to the current, some having electron-like and some having hole-like orbits, then the total current density is given by this equation, where N effective is the total density of electrons minus the total density of holes, and the Hall coefficient is given by RH is equals to minus 1 divided by N effective times E times C. In case of divalent, trivalent or tetravalent metals, part of the Fermi surface is electron-like and part of it is hole-like. If more contribution is coming from the hole-like Fermi surface, then that leads to anomalous Hall coefficient.